Hi guys, how you doing this morning?
Good, how are you?
I'm good, thanks. Did you guys all have a good weekend? It was nice and warm and sunny. So, let's see. Let me just give this a minute here. Um, so just as a reminder, don't forget that on Wednesday we have classes because Wednesday is the wellness day for Northeastern. I will actually have office hours. Some of you have emailed me and asked me about office hours on Wednesday, and because I'm getting people asking about it, that there's an interest. I will have office hours on Wednesday, so at the normal time. So if you guys have any questions that you want to ask, feel free to stop by. I'll be there from like 12:15 to 1:15. If you guys want to come by for office hours on Wednesday, it's not mandatory, but we don't have classes on Wednesday. So just kind of keep that in mind in terms of what we're trying to do. Okay. I think you guys all set with that, that we don't have school, we don't have classes on Wednesday, but we will have office hours. So today we're gonna keep talking about chapter 3.5. That's our volumes of revolution. I just go around various axes. Last Thursday, we did going around a horizontal axis, and we used a particular method to go around the horizontal axis that can be used to go around the y-axis or a vertical axis. It's not as elegant for that. We're going to actually talk today about how we go around a vertical axis, and we're going to be working through stuff like that. So this method that we're going to talk about today is really good for vertical axes. Okay. And if we have time, towards the end of class, I'll answer questions on homework for 3.5. Like I said before, I do want to call your attention to my YouTube page. You take a look, I have two playlists for Calculus 2. One of them is the lecture videos, which I post up all the time now as soon as I have them for this class. The other one is a set of videos that I made a year ago when we went on lockdown that basically pick up in chapter 3. And so I've got a lot of videos about chapter 3.5 homework, different types of revolutions, different types of questions. So you can take a look at the playlist for Calculus 2. It's like example videos. You can take a look for those. If I remember, that's what it's called, example videos. So that I've actually have like a lot of homework problems and old exam problems. That'll be really helpful for the final exams because for the final exam, because I went through and did a whole bunch of final exams last year. So there are a whole bunch of videos for that. And obviously, we'll still be going over things in class, but if you want like additional resources to take a look at, the YouTube page has a lot of stuff up on there. Okay, so kind of keep that in mind for things that you can take a look at for extra stuff. Okay, so with that said, let's go ahead and keep talking about chapter 3.5. Let's see if I can make sure this is all in focus. So chapter 3.5, so this is still volumes of revolution. Okay, and this is, we're gonna do part 2, which is called the shell method. Okay, so this one is really good for rotating around a vertical axis. I'm using these terms, rotating and revolving, kind of synonymous. Rotating, revolving around a vertical axis. So in this case, we're going to see things like we're going to go about the line x equals some number, right? Or we're going to go about the line y-axis. Be really careful. I see this a lot in quizzes and exams. People see, like the question will be phrased, you're going to take this equation and rotate about the line x equals 3. Say, for example, people will often draw a really nice picture, but they're going to draw it as y equals 3, which is the horizontal axis, and then you have the whole problem wrong. So be very careful. X equals 3 is a vertical line, right? You're going to count out to where x equals 3, and you're going to draw a line that goes like this, right? And that's going to be your axis of rotation. Remember, we're going to draw a lot of pictures so we can help ourselves visualize what we're trying to do. So keep that in mind. Be very careful when you're plowing through these problems, especially like on a quiz or a test when you're going really fast. you know, that you take a moment just to think about, well, what does it mean? X equals 3, what does that look like? It's going to be a vertical line. Okay, it's parallel to the y-axis. Okay, so the shell method, what I'm going to do is, this is kind of based on like cylinders, right? So let me break this down. So we're going to break our solid into various like outside, we call it the shells. I always think of like a seashell, but it's not a seashell. It's just like a hollow shell, like just like a container, like when you open up like a Cheerios box, or when you open up like a Pringles can, you know, it's nice and cylindrical, right? I've got this cylinder here. It's just basically this circle, right? So break our solid into hollow cylinders. Okay, so it's going to look like, if I just break it in, I'm going to take a look. I'm going to really zoom in. So I've got this shape, right? And I'm going to draw this. I'm going to over exaggerate this thickness right here. So here's our thickness of our cylinder, right? And let's draw this out. Oops. And then it's going to look like, I've got my inner circle, and I've got my outer edge, and I've got my inner like this. And so this thing is going to come down to here and kind of get a feeling for our shape here a little bit, hopefully. Like I said, I'm not a great artist, but I do my best. So this here is our height, right? This here is our width. This is going to be our delta R. Okay, this is like our dx, right, or dy, right? Well, in this case, we're going to be doing dx. But this is our delta. This is our thickness. This is infinitely thin, right? When we do these integrals, we're gonna integrate up. We're gonna create this hollow shell. We're gonna create another hollow shell and another hollow shell and another hollow shell. They have this. They're like infinitely thin, like potato chip slices, right? Infinitely thin slices right here. Okay, so that's our thickness here, and then we've got this radius. Right, we also have like an inner radius here too, but the radius, I'm writing this really small, but the radius and the R are basically equal to each other, right, when the thickness gets to be really small, as delta R goes to 0, right? So this is basically equal to this one as this one goes to 0, okay? So when we want to think about this, okay, so if I want to think about my volume, okay, so the volume is going to be, I've got 3 pieces to the volume, right? So the 3 pieces to the volume of our, we'll do this, of our cylindrical shell, right? This is like your soup can, right? It's just this round soup can, okay? It's just a shell, okay? The volume of this is going to be like approximately equal to 2 pi r. So this is our diameter. So let's write this down. Our diameter, right? So that's 2 pi r. That gives us our circumference. Sorry, this is 2 pi r, and then our times pi equals our circumference. Okay, times our height, okay, times our thickness. Okay, so I have our 3 measurements here, right? I've got my my circumference all the way around. So 2 times r gives us our diameter, times pi gives us our circumference. So the circumference times the height times the thickness gives us a volume, right? What am I going to do? It gives me a volume of this really, really thin shell. Well, I'm going to take all those thin shells and I'm going to add them up as I go from here to here, from A to B, okay? So now we want to think about, let's draw this in our axis. So if I draw this as a X and Y axis, so here's my X, here's my Y. This is the thing that I'm going to be rotating around, right? Let's get this back up here. I'm going to be rotating around. So you can imagine I've got A to B. Now let's draw this out like kind of like in a shadow here. I've got minus A, minus B. This is just for point of reference because we're going to integrate from A to B. But say I've got some function, right? So here's our f of x. Okay, but what I want to do is I want to take this. So from here to here, okay, this is our function that we're integrating from A to B, right? And so this, as I sweep this out and around, you can imagine, let's draw this kind of like complementary over here. So it's going to go, here's our mirror reflect. You can imagine I'm only drawing this so that I can visualize as I go around, as I sweep this thing around in a circle. Okay, which means I've got this right there. So my hollow shell, let's draw this out. So my, right, so then, and you can imagine it's going to be sweeping out and around in the back. I don't even know if you guys can see that orange at all. Trying to create this three-dimensional shape here on a two-dimensional page. Right, you can imagine as it's sweeping around, it's creating this, and it has like this hole in the middle, and that comes from the gap between A and our axis of revolution. Okay, but I've got this shape that I'm circling around. Okay, so you can imagine here's our function, right? And then let's draw this out as, I've got this tiny little bit right here. This is our thickness, right? This is going to be our delta x, right? Or what's going to become our dx as we integrate. Okay, so that's our thickness of that shell that we're going to take this, we're going to rotate it all the way around our axis of revolution here. Okay, but this f of x, right here, that gives us the height of our function. So f of x gives us our height. Okay, sum up all of these like circumferences times the height times the delta x to get the volume, right? And when we do this, let's also remember our height is equal to the function at that particular x value. Kind of like what we did with the disk method, right? Our function represents our height. Okay, so we want to start thinking about how do I make this as the volume of revolution. Okay, we'll just do, this is a vertical axis. In this case, we're going to do the y-axis. We're going to go through different examples. If I go around different vertical axes, what is my radius going to look like? Because the radius may change depending on what we go around. So my volume is equal to, I'm going to go from A to B, right? So A to B tells me which portion of my function I'm operating with, what shape am I rotating around the vertical axis. So I have 2 times pi times my radius times the height of the shell times our dx. This is our thickness, dx, right? So let's plug in r. So this is equal to, from A to B, 2 pi, our radius. Now let's remember, right, my radius is equal to that x value, right? So as I go out here, as I go out here, that x value, where am I in the x location? That tells me what my radius is. So 2 pi x times the height of the shell is our function. Dx is our thickness. Okay, so this is your volume right here when you go about a vertical axis. And I'm going to put a box around this whole thing here. And we're going to work through a number of examples so that you can see what this whole thing looks like in practice. How we calculate the radius may change depending on what kind of vertical axis we're going around. We're going to go through a whole number, like I think like 5 or 6 different types of like sort of proto examples, so you can see how the radius may change, okay, and like how we work through our thought process on it. Okay, our lecture examples for this second half, right, of 3.5 are going to contain a lot of examples, but also some note type of things too. Okay, so volume of revolution, our 2 pi, basically 2 pi r. So this is our circumference times the height times the thickness gives us the volume, and we're going to sum up all of those tiny circumferences, all those, you know, as I go from A to B. Okay, and that gives us our volume, overall volume. Okay, and remember, like, I'm not a great artist, but these visualizations will help you, especially if you draw the axis that you're rotating around. Okay, it'll help you picture like what you need to. Here, remember, x equals some number. We're going to go about the line x equals 3. That's a vertical line. Okay, if you're going to go about the line y equals 4, that's a horizontal line. Okay, so keep those in mind. And it feels like, why is Dr. Wilson repeating that? Something seems obvious, because I see that mistake again and again and again on the quizzes and the exams. All right, so examples. I'm looking at our lecture examples. So I scanned in the first part using the disk method, and now we're gonna, I'll scan in the rest of it for part 2, which is gonna be our shell method, okay? So find the volume of the solid obtained by rotating the region of the graph, this function here, about the y-axis. So you remember the last example that we did, example 3, basically we had this function that went about the y-axis, and we could actually, you know, rewrite the function to solve it in terms of x equals some function of y, and then we could use the disk method, right? You can imagine y equals this thing here. If I were to try to rewrite this in terms of x equals something, it's going to be too complicated. So whenever I see a function that says I'm going to go about a vertical axis, I just think shell method. It's very straightforward, so I'm going to use that. So shell method. Okay, so don't even worry about it. Even if it looks like you can convert it and you can, you know, change the bounds of integration, you can go dy and all that. If you're going about a vertical axis, just use the shell method. It's very straightforward, okay, when you're trying to do this. And I forgot to tell you the bounds of integration on this. So this one goes from 0 to 1. That was a typo on my part. I forgot to give that to you. Okay, so we're going to go about the y-axis from 0 to 1. We're going to take this function here. So, you know, I like to graph things out. Whoops, I didn't give myself enough room. So I graph these things out. Okay, so I'm going to go, here's 1, here's my x-axis. I'm just going to write -1. Here's my y. Now I'm going to put a little marker, right, to remind myself of what axis I'm going around, right? All right, so this thing, if I were to plot this, it's going to look like, this is 1. It's going to, it kind of looks like, it goes up and does other things, but basically it goes, makes this nice shape like that. So I'm going to draw really lightweight, like a real kind of like a, that's just going to give me a visual, so that when I take this and I circle it around, I'm going to rotate it around, I'm going to get this, okay? Which means that I'm going to get this thing kind of, it's going to look like a circus tent as I rotate around the y-axis. Okay, so I'm taking this thing, or like, you know, it's going to look like a tent, right, as I go around. Okay, so now this is our function right here. F of x, this is our function. So maybe I'll make that a little bit darker so you can see right there. So our nice function. Okay, from 0 to 1, right? That's the part I forgot to give you before. Okay, now we're going around a vertical axis. So I'm going to do my shell method. So my volume is going to be my bounds of integration, 0 to 1, 2 pi. Now let's think about our radius, right? So our radius says, I'm going to start here. I'm going to go from 0 to 1. So that means that this is my radius, right? So wherever I'm at, like this right here, I'm going to spin around in a circle. If I'm here, I'm going to spin it around. Here, I'm going to spin it around. So wherever I'm at in x, that is my radius. My height of the function, right? My height of the function right here. This is our radius. This is our height. So here is the height. Here is the height, here's the height, here's the height. So our height changes and our radius changes as a function of where we're at along the x-axis. So my height, right, f of x, we're going to fill in the blanks in a minute. Okay. All right, so let's fill in for our, I'm going to go from 0 to 1, 2 pi x. My function, 1 minus 2x plus 3x squared minus 2x cubed dx. Okay, I'm going to distribute, actually I'm going to factor out the 2 pi, and then I'm going to distribute the x to all of these terms. Okay, and then I'm going to integrate with the power rule. So you can see how much nicer this is if I'm going around a vertical axis, right? Because it's pretty straightforward in terms of what I need to do with my functions. This is going to be 2 pi, 0 to 1. I'm going to distribute, so it's going to be x minus 2x squared plus 3x cubed minus 2x to the 4th dx. Okay, so all I did was take that x and distribute it to all of these here. Okay. Right, now we're just going to integrate using power rule. So it's going to be 2 times pi times, this is going to be 1/2 x squared minus 2/3 x cubed plus 3/4 x to the 4th minus 2/5 x to the 5th. And we're going to evaluate from 0 to. Remember, on these, you have to show the antiderivative. Sometimes on the test, we'll ask you to set it up but not solve it. Oftentimes for these, we'll ask you to actually go ahead and tell us what the volume is, because these are mostly fairly straightforward in terms of integrating. But when you're doing this, you must show us the antiderivative in the equation form. I know a lot of your calculators will give you an answer for this, right? If you plug in, my calculator will do it, and it's pretty old. So you have to show the antiderivative so that we know you know how to integrate things. All right, so I'm just going to evaluate it. I did it offline. This is 11 out of 30 times pi. When in doubt, you can leave it in terms of pi, okay? Unless we told you, multiply it through. Just leave it in terms of pi, okay? So don't worry about the radius. We're gonna go through a whole bunch of examples to think about that on the shell method. How you guys doing? Are you all done writing this stuff, or should I? You guys okay with this? Okay. All right. So the big question is how to choose between our disk washer method and the shell method. Right? I've got these two great methods. How do I know which one to use? Okay, so in general, sort of a general rule of thumb, you can use the shell method, like we just talked about. We're going to go through other examples. Use the shell method if you're rotating about a vertical or y-axis. Okay, so shell method for a vertical axis. And I keep trying to say vertical instead of y-axis because it could be x equals -3 or x equals +2 or x equals 0, which is our y-axis. Okay, so shell method for a vertical axis. And we're going to use the disk washer method. Remember, these are the same thing, right? Except that I'll have one function, it goes to the x-axis, one goes, they have two functions, that I'm rotating an area around. So the same method. This is circumference, this is area, right? You can kind of think about it that way. Use the disk or washer method if we're rotating about a horizontal or x-axis, okay? Y equals something, right? Y equals 0 is our x-axis. Okay, so just something also to keep in mind, this comes up a lot on our final exams. We always have a question like this, certainly on our midterm, but definitely on our final exam. And to make it complex, we usually do things like we're going to take the region between two curves, and we're going to rotate it around a horizontal and rotate that around a vertical to kind of see what that looks like. So if we want to rotate the region between two curves about, say, the y-axis, right? So I've got two curves happening, and I have a whole bunch of examples at the end of our lecture, examples about finding the area between two curves, just to kind of remember like how we need to do that. We'll go through those in just a minute, but let's say here's our x-axis, here's our y. We're going to go about a vertical axis, so we're going to be using our shell method, right? So let's say I've got one function, this is f of x. I've got another function, this is g of x. Okay, now what happens is my upper function is my f, my lower function is my g. So this area between them, say between a and b, is f minus g, right? I have to calculate the area between those two, which is the upper minus the lower. Upper function minus lower function, okay, to get the height, to get the area that gets rotated or revolved. Okay, so then basically, and that's this is the case where we do, this is f minus g because f is greater than or equal to g, right? And then sometimes, like we're told to go from a to b, if we're not given bounds of integration, we find where these two functions intersect each other, and that forms the bounds, and we take that area. All right, so in this case, we're going to get a volume is going to be equal to a to b, 2 times pi, and then we're going to go radius times height again, times dx, which is our thickness. So in this case, right, we're going to go a to b. Remember, we're going around the y-axis, so 2 times pi, right? X is our radius, and then our height becomes f of x minus g of x dx. We're going to take that area, that solid block of area, function, upper function minus lower function, and rotate that around. We would do the same thing, right? We did that before when we were rotating around a horizontal axis, right? We calculated the difference between those two. We did inner radius minus outer radius. Okay, so before we get into these radii, like the, I'm sorry, before we get into the rotation of this area between the two curves, I want to actually talk about our next set of examples. It looks like this. We've got like 1, 2, 3, 4, 5, 6, which is we want to calculate the radius for the shell method. And we're just going to basically take the y equals x squared, our basic parabola, and we're going to rotate it around various axes just to kind of see what this thing looks like as we go around. And it's important to be able to visualize because your radius is going to change. So I set up all these examples here so that we can see how it looks and how it's different. And we're going to talk about it. So these are all vertical axes. Okay, so we're going to go around vertical axes. Let's see, is that even in focus? Doesn't. Okay, that's a little better. Okay, so now let's do the first one. So I'm going to just keep drawing pictures here so we can visualize what it is we're trying to do. Y, and we're going to go about the y-axis. This is our basic function here. So we've got our y equals x squared, right? And you can imagine we're going to go from A to B. And so what happens is, let's see, I'm going to draw this here, and I'm going to take this and I'm going to swoop it around. Right, so I kind of get this bowl shape curve that I'm getting. I'm kind of getting this, you know, bowl that I'm getting. It's sort of like a solid bowl, right, as I go around the y-axis. Now my radius is simply equal to x, right, as I rotate about the y-axis. So this is just going to be a to b, x, 2 pi, and then my function itself is x squared dx. Okay, so the radius, let's draw this in red. That's our radius right there. Okay, so our simplest case, because our radius, we're going to go from A to B. So this right here is our radius as we go. Okay, so wherever I'm at in my x, that tells me what my radius is. Okay, I'm going to be plowing through these here. So we're going to do the same function over and over again. Okay, so now let's think about it. This one's going to go, we're going about the line x equals 2. So let's draw this out. This goes way out. So 1, 2, x equals 2. And we're going to go from a equals 0. So here's a, here's b equals 2, because this is going to change too, depending on what a and b are, right? It's going to look different. So let's draw this. So x equals 2 is our axis of rotation. X equals 2, so I'm going to draw a line like that, okay, as I go around it. So now my parabola starts here, and it goes like this, right? So that's my parabola. So now what happens is I'm going to take this function, right? I'm going to take this stuff, and I'm going to rotate it around. So this is the piece. Let's see, I'll draw it here in red. This is the piece because I'm going from a equals 0 to b equals 2, right? And so I'm going to rotate it. You can imagine I've got a little piece here. Here's my 2. So this is 4. I've gone 2 units out from my center here. This thing is going to get swept out in the back like this. So it's going to look like that. This is the piece that we have here, right, as we go around. Okay, so now our radius in this case, right, we're going from A, we're starting here, and we're going out to our axis, right? So my radius is right there. Okay, so my radius rotating about the line x equals 2, so it looks like this. I'm going to go my radius is equal to 2 minus x. And I do this little check, right, where I say when x is equal to 0, I'm at the maximum radius. My radius is equal to 2. When I'm going to go part way. So when x is equal to 1, my radius is equal to 2 minus 1. So my radius is equal to only 1 unit. When x is equal to 2, when I'm right here, my radius is equal to 0. So these are ways that I can help myself think through how I'm going to do this, right? So now my volume is going to go from A to B to pi 2 minus x times x squared dx. So this is our radius right here. Okay, and now I need to multiply that. I need to multiply x squared times both of these terms, right? Like if this was a more complicated function, I'd have to distribute it, like I'd have to FOIL it or do other kinds of distribution, okay? So I'm going from A equals 0 to B equals 2, and I'm rotating about B. B is our axis line, okay? These are all different like permutations for how we can think about how to rotate around this. All right, same function, x equals 2, A equals 2, which is our axis line, and B equals some other number, right? It doesn't even matter. Let's draw it out. So, and then this is our y-axis. This is our x-axis. This is our y-axis. Now I'm going to draw my parabola like this, right? This is y equals x squared. And now what we're going to do is x equals 2, right? And then A equals 2. So this is A. This is still our axis line. I'll draw this in green. Okay, so that's where we're going around. This is x equals 2. Right, so that's our axis line. And we're going to integrate from A equals 2 to B equals some other number. So like we'll just go out to here. So this is B. Okay, so the thing that this is the piece that I'm going to be rotating around, right? So it's going to look like, let me draw this in. And then I'm going to get like a circle around the back. Okay, so my shape as I go around, okay, looks like that. Now, let me see, I'll draw this in orange. This is the piece here that we're taking and we're rotating it around. Okay, I know this looks really complicated, but we're going to have it in our notes and you'll have it to think about. Okay, so we're rotating around line x equals 2, right? This is our, and that's our A. Okay, so now what we're going to do is we're going to say, we're going to write down what our radius is and we're going to do our check. Radius is equal to x minus 2. Okay, and we're going to see why. So it's different than what we had before, right? Let's do our quick check, right? Because we start at 2 and we go out to some number, right? So our radius is, this is our radius right here. We start at A, we end at B, so our radius is here. So our check goes like this. When x is equal to 2, our radius is equal to 0, right? I'm just right here. I'm rotating about this line. When x is equal to, say, 3, right to here, our radius is equal to 1 unit. Like if x is equal to b, okay, like if x is equal to b, then our radius is going to equal to b minus 2, okay, whatever that is. So now our volume, okay, so you can see our radius is getting bigger essentially as we're moving from A to B. That's how you want to be thinking about it. So our volume, we're going to go from A to B. Always A to B is your bounds of integration. 2 pi, because we're doing circles, our radius, x minus 2, times the height, which is our function, times dx. Okay, so this is our radius. Okay, different permutations on this. It helps to think about it. The checks help you a lot, help you visualize my radius should be getting bigger as I'm heading out towards B, because my A is my axis line. All right, so let's say, okay, we're going to rotate about x equals minus 2. So let's draw this out. Okay, so this is my x-axis. A equals some number, so I'm going to write A equals some number. So here's A, here's B, B is some number, and then I'm just going to draw this like, let's pretend, you know, A is, doesn't matter what A is, but here's our y equals x squared, and then we're going to rotate about x equals minus 2. So now we're talking about a negative, our axis of revolution is in a negative. Right, so this is where we're heading around. Okay, so what this is going to look like, right? I'm taking this bit, this piece here from A to B, right? And I'm going to take that and I'm going to rotate it around. So I'm going to calculate out my difference between here to here, and I'm going to go, this is going to be like, say if A equals 2, say for example, this is going to be minus 4, and then this is going to be my sort of my mirrored B image right there. So then now this is going to look like, I'm going to take this and I'm going to rotate it around so it's going to look like kind of a mirrored image. Like that. And as we go around. Okay, so this thing, let me draw this. Right, so I've got this bit right here. Right, so we're kind of creating this bowl shape, okay, as we go around. Okay, as I go around this. So let's think about what our radius is going to be now. So our radius is going to become, right, my radius actually goes from here all the way out to here, to here, to here. So this whole thing is my radius, okay? But I only want to integrate from A to B, right? So A to B, when I integrate from A to B, that handles the fact that even though this whole thing is my radius, right? I'm only taking this volume here from A to B. So my radius is going to look like x minus a minus 2, which becomes x plus 2, right? And you can do your check, right? So when x is equal to, you know, x is equal to minus 1, right? Our radius is going to look like it's minus 3, but I'm only looking at integrating from A to B, okay? When x is equal to, like basically I'm only looking at like when x is equal to A, okay? So A plus 2 is my radius. When x is equal to, say, I don't know, 3, for example, I'm going to go 2 plus 3. So I have to take into account this distance and then this distance right here. Okay, so then my volume is going to equal from A to B, 2 pi, x plus 2, x squared dx. Okay, this is if we're rotating about the line x equals minus 2. This may seem confusing, but write it down, right? Try to copy down the pictures. I'll scan these in later so you can take a look at my wonderful artwork. And then you'll have it to kind of visualize when you're working through problems. I know it's a lot to take in, okay, a lot to think about, all these different radii, but this is just kind of like a thought. These aren't like real examples, but they're just thought problems for how you calculate the radius, okay, how you think about it. So 2 more, and then we'll move on. So question number 5, this is example 5. So we're going to take this, we're going to go about the line x equals minus 2. our A is our axis line and B is some other number. Okay, so this ends up looking like, so remember A and B before were not our axis line. We were looking at A and B over here, but our axis line was here. So I had to calculate out that distance plus our radius. So this, let's go ahead and draw this out too. See, here's our y-axis, here's our x-axis, here's our B, say for example, here's our A, this is our axis line. So I'll draw up a, right, remember you always want to put down like where you're rotating around just to kind of keep it together. So this is, I'm going to draw this, it's going to go like that, y equals x squared. Okay, so our radius now, our radius is there. Okay, so now what happens is, right, I've kind of got this little piece here, right, and I'm going to be taking this as I rotate it around. So this is going to look like, as I go around. So I'm going to go x is equal to minus a, right? A is negative, okay? So we're going to rotate about this line. It's really x equals a, but a is negative. So I'm going to write out like this. So I'm going to say my radius is equal to x plus 2 again, right? Because what's happening? So our check says when x is equal to 0, our radius is equal to 2. So when x is equal to 0, right, we're going about this line, our radius is at its max, okay? When x is equal to minus 1, right, we're right here. When x is equal to minus 1, right, our radius is equal to 1 unit. When x is equal to minus 2, our radius is equal to 0, okay? And our volume is going to be the same thing, right? We would just, volume, we're going to go from A to B, say for example, 2 pi x plus 2 x squared dx. Okay, lastly, right, we're going to go about the line x equals minus 2 and B equals minus 2 is our axis line. Okay, so let's just draw this out. So B is some negative number, right? Let's say B is equal to minus 2. This is our x equals minus 2. So our axis line is equal to B. Sorry, you can't see what I'm writing. Is equal to B. And then now our function is going to go something like this. So we can get this to draw out right. Y equals x squared. Right, it's a very poor parabola. Bear with me here. All right, so we're going to go to from A to B. So I'm looking at taking this piece and this piece. Right, and I'm going to spin it around x equals B. So it's going to go around this. So it's going to look kind of, I'll do it right here. So let's, right, and then we're going to go. Okay, so we're basically creating this shape here. It's not my, like I said, my drawings aren't glorious here, but so we're going to rotate around x equals B. B is negative, A is negative. So our radius is going to end up looking like minus 2 minus x, right? So our radius goes like this. So here's our radius, okay? So if we do a check, so when x is equal to minus 2, our radius is going to equal to minus 2 minus a minus, which which becomes 0. So when we're right here, our radius is going to be 0. Okay, when x is equal to -3. So -2 minus a minus, so our radius will be equal to 1. When x is, say, -4, -2 minus a minus, our radius is equal to 2, right? So our radius gets bigger as I move farther out, okay? And again, our volume, we go from a to b, 2 pi -2 minus x squared dx. Kind of work your way through it. Phew, a lot of things to think about. Okay. I'm going to go through a couple examples on this next bit, which is about calculating the area between the two curves. I'll fill out the rest of the lecture examples for that. We'll just do like, we'll just choose a couple. And then we're going to do, this is just basically like a review, hopefully, of things that you did in Calc 1. But it's a way of thinking about the area between two curves so that you can work it from there. I think what I'll want to do is, I think I'm going to pick and choose the things I'm going to do. Your graphing calculator is going to help you on these. Like I said, I'll actually do these out and I'll scan them in. So, because I'm only going to pick a couple. So I think example 6 is going to be probably more indicative of what you might see on like an exam. 6 or even 8, say for example. So I'll do 6 and then I'll do 8. These are just areas between curves. Okay, so this isn't rotations. These are the things that you're going to rotate around a y-axis or around an x-axis. Okay, so don't worry that I'm not doing them all. I'm going to do them all like offline and I'll scan them in, but I just want to kind of give you a heads up. So we've got these two graphs here, g of x equals x and f of x equals 2 minus x. And so we're not told calculate the area between two curves. We're not given a bound, which means that we have to look for where they intersect. Now, you can use your graphing calculator for this if you want. If you do use your graphing calculator for this, make sure you write down, I use my graphing calculator, but you want to, at least set up these equations, right? Where I'm going to set them equal to each other. 2 minus x squared equals x. This is just quadratic, so I can actually just solve it, right? So I'm going to bring over my x squared. I'm going to bring over the 2. See, for example, and what are we going to get? X squared plus x minus 2 equals 0. I'm going to solve for x. I'll use the quadratic formula for that. So -1 plus or -1 minus 4 times 1 times -2 all over 2 times 1. So it's going to give us x is equal to -2 and +1. These are the places where f of x and g of x intersect. If I were to graph these two out, I would see it also. So let's go ahead and graph. I'm just going to do a quick sketch here. X-axis, y-axis. Let's see. 1, 2. So here's our g of x function. And then this one looks like it's a downward parabola. And I think it goes here and here, kind of goes like this, and these two intersect here, so I'll do there. So basically, and this is our g, this is f of x, and this is g of x. So, right, so we've got this area here. Okay, so these bounds right here, where x equals -2 to +1, are going to form our bounds of integration if we're calculating a volume, right? So if I was going to take this and rotate it around like a horizontal axis or an x-axis, I've got, right, my upper function minus my lower function, right? So to get the area, between the two curves, right, what are we going to do? We're going to integrate from -2 to +1. That gives us that total area, right? I'm going to do upper function 2 minus x squared minus my lower function dx. right? So this is, let's write this in a different color. This is upper minus lower, and it doesn't change along the way. We'll do another example where they're going to change. So now it's just, you know, combining like terms and integrating, and then basically we're going to get minus 2 to 1, 2 dx minus, right? This is going to be x squared dx minus x dx, which gives us 2x minus 1/3 x cubed minus 1/2 x squared minus 2 to 1. And then when we do this, we find that the area is equal to 9/2. So that's just simply the area. I'm just reminding you about how to do the area, okay, between the two different curves, okay, because often what will happen on an exam, like on a final exam, these are really common questions on final. We're told to find the volume of revolution about like the line, say y equals 3, or the line, you know, x equals 4, or whatever, and we've got this, you know, region between the two curves. Sometimes we'll have two different questions on an exam where we've got these two functions, and we say part A is what's the volume of revolution when I go about the line y equals 4, and that's going to give me a horizontal axis where I'm going to get a volume. I'm going to take this funny shape and I'm going to get a ring this way, right? And then part B will be what's the volume of revolution when I take these two functions, right? And I rotate them around a vertical axis, like around the y, maybe not the y-axis in this case, but maybe about the line, you know, x equals -2 or x equals +5 or whatever. You get the idea. We're going to rotate it around. We're going to take this and we're going to get a ring going this way, okay? So you need to be able to find the area between the two curves so that you can take that and form a solid block, and use the two methods appropriately, okay? So what I'll do offline, I'll go and I'll actually fill in the rest of these lecture examples here so that you have them, so you can visualize, you know, how you remember how you calculate the area between the two graphs. Okay, especially like on a question 8 where like the the area is going to change because I have to break it up into a couple different integrals. So I'll do those offline and I'll scan those in. I don't want to spend too much time on it. So in case you guys have questions on homework problems, I want to spend some, we've got about 10 minutes. I want to spend some time answering questions on homework problems for 3.5. But anyway, so you can take a look for that, and then I'll put those up later. Okay, so this is just kind of a review from Calc 1 topics. Okay, all right. So that's 3.5. There's a lot of stuff in there. I can imagine that once you guys get started on the homework problems, you're going to have questions. But if anybody has a question on homework problems for 3.5 right now, you want to ask, I'm more than happy to. 51, you got a negative volume. Let me see. I don't think you should be getting a negative volume. Let's see how you calculated the radius. 51. Yeah, so let's go ahead. We'll do that one. That's a shell method. I assume you're asking if I can do that one, right? So this is homework for chapter 3.5, number 51. Could you put up a list of chapters that are going to be on the second midterm? So it's basically just chapter 5 and chapter 3, right? So when we, at that point, it's just essentially chapter 5 and chapter 3 that you're going to be having, but there's a lot of stuff in chapter 5 and chapter 3, so keep that in mind. All right, so we've got the function g of x equals e to the minus x squared, and we're going to go from 0 to infinity. Okay, calculate the volume. So this is, right, this is going to be an improper integral. So when you're thinking, right, I'm going to go from 0 to infinity, I should be thinking right away improper integral, right, when I do this. Let's see, line below the graph of g of x and above the x, and we're going to go about the y-axis. Okay, so when we go about the y-axis, remember, you should be thinking shell method, okay, because that's how you want to be working your way through it. So let's go ahead. I'm just going to do a quick sketch, right, so we can visualize. Here's x. Here's y. So look, we're going to write there. I'm taking notes as I go. So this e to the minus x squared, right, starts off when x is equal to 0. This whole thing's equal to 1. And it kind of goes like, and you can even plot this out on your calculator, but it looks like here's 1, here's 2. And then the rest of it kind of cruises right along the x-axis. It's asymptotic, right? So we've got -1, -2. It's going to be mirror image here. So I'm using that as a mirror image to help me. I'm going to take this, right, and I'm going to go around. So I've kind of got this like smooth, like you know when you crack an egg and you put it in a plate, right? It kind of has this like the egg yolk flowing out. I have a lot of food examples. I love food. All right. Right, so we've got this thing that we're getting, and then it goes out in the back. Okay, so this is what we're looking at. So this is the volume that we're going to be trying to figure out. Okay, see if it works. So let's calculate. So volume, we're going to go from 0 to infinity, 2 pi, right? My radius is x. X is my radius. And then my function, my height, is e to the minus x squared dx. This is our shell method. Okay, which means I need to convert this into a limit process. I'll take out the 2 pi outside the limit. So it's going to be 2 pi limit b goes to infinity from 0 to b x e to the minus x squared dx. It's actually really convenient that the x is there because that means I can integrate by substitution, right? Right, so my u is equal to minus x squared. My du is equal to minus 2x dx. Well, I have a 1x dx. I'm going to divide by minus 2. So I'm going to say du all over minus 2 equals x dx. So I'm going to substitute that with du over minus 2. Substitute this with u. So this is going to look like 2 pi limit b goes to infinity, 0 to b, e to the u, du, right, all over minus 2. So I can take out the minus 2. So this looks like it's going to become minus pi, right? Because I've got the minus 2 and the positive 2 becomes minus 1. Limit b goes to infinity, 0 to b, e to the u, du. So when we integrate this, we're going to get minus pi limit, right? I'm going to get e to the u, and I'm going to substitute back minus pi limit b goes to infinity, e to the minus x squared, and I'm going to evaluate from 0 to b. Okay, so let's go ahead and evaluate that. So that's going to be minus pi times e to the minus b squared minus a minus pi e to the minus 0, right? So this is actually minus pi, right? This is times 1 over e to the infinity plus pi times 1. Okay, this right here, that goes to 0. So this volume equals pi. You wouldn't have thought, right? We had to work through all the math to see. Yes, we can do number 10. I will get that set up while you guys are taking a look at this. And then I'll show you my graph for number 11 too. Number 11 is good. You gotta do so. You guys all set with this? Okay. Okay, let me turn the page. Okay, so number 10. Number 10 says we're going about the we're given the function above the x-axis. So I'm going to say y equals sine of x. We're going to revolve around the x-axis. We're going to go from 0 to pi. Okay, so the first thing I'm going to do is I want to plot out what's my sine function look like. So here's my x-axis, I'm going to remind myself what I'm doing. Right, so my sine function between 0 and pi looks like that, right? So I'm going to take this, I'm going to rotate it this way. Right, and then I'm going to rotate it back. So it's going to go, so I'm going to basically create this like circle as I go around. Okay, so I'm going this way. I'm going to try to draw my little lines based on the direction of rotation. kind of creates a football shape, right? Football-ish. So this is, right, we're going around a horizontal axis. So this is going to be our disk method. Remember, we have circles. I've got a circle and a circle and a circle. I've got to stack up. So this is pi r squared, our area. We're going to add up the areas. So our volume is going to go from 0 to pi. They told me what my bounds were. Pi r squared. My radius is the function sine squared x dx. Or I actually, let me write it like this, sine of x squared, so you can see it better. Okay. So now I have, this is pi 0 to pi sine squared x dx. To integrate this, I'm going to use an identity. Right, so my identity, sine squared of x is equal to 1/2 minus the cosine, oops, sorry, there's a 1/2 in there, cosine of 2x. This is 1 minus cosine of 2x all divided by 2, right? So maybe you've seen it like this. Right, so you can now do u substitution when you go to integrate it. So our volume is going to look like pi 0 to pi. It's going to go 1/2 minus 1/2 cosine of 2x dx, which is equal to pi times from 0 to pi, sorry, 1/2 dx minus 0 to pi 1/2 cosine of 2x dx. Okay, which when I go to integrate it, I'm going to get pi over 2x minus pi over 4 sine of 2x. I did use substitution right there. I'm going to evaluate it from 0 to pi, which becomes, right, so I plug in for x now, right, so this becomes pi over 2 times pi minus pi over 4 times the sine of 2 times pi minus 0 for x, the sine of 0 is 0, right? Sine of 2 pi is going to be 0 also, right? So I'm just basically going to be getting pi squared over 2, which if you want a decimal is like 4.93. You should leave it in terms of pi. Okay. Then I'll set up question number 11. In previous semesters, a lot of students had questions on number 11. What region we're actually looking for in terms of the area. So I'll just start setting that up so you can see what that looks like. We had a lot of discussions about what they were trying to do. Y equals x squared plus x plus 1 and y equals 10, and we're going to go 0 to 2. So we're revolving around this axis y equals 10. So it's going to look like, sorry, you can't see that. Here's my x-axis, but y equals 10 right, is a horizontal axis. So this function here, right, starts here and it goes up like that. So this is 1, this is 2, and then it's going to look like this on the flip side. So I've got this piece, right? And so what's happening is what I'm trying to get, because I want to get this area here, because they said the area between the function and the x-axis. So the area that we're actually I'm going to take this and I'm going to rotate that around. Okay, so I've got this, so it creates an outer edge. So this is, okay, so then my area of rotation is like this. Okay, so basically I've got this like a hollow piece on the inside, and I've got this stuff, this green piece right here gets rotated around. So this equals, you can imagine, watch what I'm going to do. I'm going to take y equals 10. I'm going to take this whole distance here, this solid block. I'm going to rotate this around, right, from x equals 0, I'm sorry, y equals 0 to y equals 10. And I'm going to rotate it around. So I'm going to get this solid circle as we go around. Okay. Now I'm going to do that, and I'm going to subtract. What are we going to subtract? We're going to subtract as though I were taking my parabola and then rotating it about y equals 10. So I'm going to subtract this bit, right? So if I were to take that and rotate that around, and that's how I'm going to get this hollow shell. So I have a solid piece minus this inner piece here, and it's going to give me that outer piece. Okay, this is a lot going on in that one. But I think I've got this one worked out in a video if you want to see it ahead of time as you're working it through. We've actually run out of time, and I can't keep you because I actually have a class too. You can come to office hours, and we can go over all these things. Okay, but this is how you want to set up number 11. I've got this area, this volume minus that volume. Okay, and then we'll go over these things on hopefully in office hours. And so I guess I'll see you guys on Thursday. Okay, if I don't see you in office hours. I have office hours on Wednesday though. So if you want to come by on Wednesday, I'm more than happy to talk. Okay, talk about stuff in addition to today. Okay, guys. Have a great day. I'll see you later.
Thank you.
Bye.
Thank you.
Yeah, Lauren, that's a really great question. Is there a quiz this week? I'm wondering about that. We were originally gonna have a quiz on 3.5, and I do actually want to have a quiz on 3.5 because I think it'll help you. And maybe I can just choose problems that are on the DISC method, things that, basically just look like a DISC method. I'll send out an announcement about that so we can talk about that. I think you guys just learned the shell method today, so maybe the quiz will just be on the DISC method, but I think it'll help keep you guys up to date on stuff. I know it seems like a pain, but it'll help prepare you for things. Okay, I'll send out an announcement for it. Okay, bye guys, have a great day. Enjoy your Wednesday off from classes.